Hey guys, welcome to our Friday lecture. Just a little bit late, I was busy with the exam last night. So we were looking at drawing our Lewis structures, and we had said that we sometimes have these molecules with hypervalent central atoms. And those hypervalent elements break the octet rule. And there were three hypervalent elements that we were looking at right next to each other in the periodic table. We had phosphorus, which can sometimes be 10 electrons. We have sulfur next door, which goes a step further and can be as many as 12. And then chlorine next door to sulfur, which again raises the stakes by another 2 electrons and could be as many as 14. So we had said that to work out what the correct configuration was, the correct Lewis structure, was to work out when the hypervalent element itself lost its electrical charge. Once it doesn't have charge, we've got to the correct Lewis structure. And we went through that with perchlorate on Wednesday last time. So let's take a look at some more to try and hammer this home. So next example, now your notes have the actual answer already written there, but I thought it'd be more fun or more useful to actually build up and work through that answer together. So with the chlorine trifluoride, we get an electron count going. Let's see, I don't want that flashing thing right in the middle of the screen. So we do our electron count, of course. Chlorine, that would be 7 electrons because it's the 7th element in the 3rd row of the table. Fluorine also has 7 because it's the 7th element in the 2nd row of the table. And there's 3 of them. That gives us a grand total of 28. 28 electrons to make a molecule. Now, because it's the hypervalent chlorine at the center, we'll connect it up to the 3 fluorine atoms. Sometimes with the hypervalent elements, they are breaking a rule for choosing the central atom. But if that's the case, I'll just tell you. In this case, chlorine is needing the same number of electrons as fluorine, but it's lower in the table, and therefore should be more likely be the central atom. So 2, 4, 6 electrons takes us down to 22. We use the remaining electrons to complete octets, starting with the outer atoms first. So starting with the fluorine atoms on the outside, adding 6 together with the bonding electron pair to make an octet 8. That uses 6, 12, 18 more. And so we've got 4 electrons left, and they should go on the central atom as lone pairs. So do we have any more work to do? We've got 2, 4, 6, 8, 10 electrons so far, but because we know that chlorine is hypervalent, it could be as many as 14. So do we stop or continue? We check for charge, the periodic table, count compared to the Lewis structure share that we've drawn. So the periodic table, as we've already predicted, 7 electrons for the chlorine atom, together with 1 that it normally borrows to complete its octet. And so as we look at the chlorine here, it controls 1, 2, 3, 4, and then 1 from each bond, 5, 6, 7 of the electrons around it. So no formal charge. And so we know to stop when there's no charge on the chlorine atom. So nothing else to add, no extra bonds. Next one with the sulfite. That's one of our polyatomic ions from chapter 3. Electron count would be 6 for oxygen, 6 for each, sorry, 6 for the sulfur. Oh, what's wrong with me today? 6 for the sulfur, 6 for each oxygen, and there's 3 of them. And then there's that charge as well, telling us about a surplus of electrons. Things are only negatively charged if they have more electrons than protons. So 2 electrons added to our count. Oh, excuse me, those peanuts getting to me again. So our grand total electron count is going to be 26. We choose sulfur as a central atom because it's bigger than an oxygen. And just as we did before with the fluorines, we connect those atoms to the central atom using 2 electrons at a time, then completing octets as we did before, needing 6 electrons added to each of the oxygen atoms. That takes us down to 2 electrons remaining after adding 6, 12, 18. And from there, we can put that last pair of electrons on the central atom. Okay, excuse me, just a request to play dollies with my daughter. So that's on my list for later. So that lone pair on the sulfur itself, which extinguishes our supply. Now the sulfur does have 8, but remember it's hypervalent. It can be 8, 10, or 12. Does it have a formal charge? That's the periodic table count compared to the Lewis structure share. All of the lone pair electrons, but just half of the bonding electrons, with 2 electrons in each bond. So it's a 6th element in the 3rd row, as we've already deduced. And from the Lewis structure, 1, 2, 3 of the 6 bonding electrons, then the lone pair, that gives us 5. We've got a formal charge on the sulfur. So that means that we need to turn a lone pair from one of the oxygens, any one will do, turn a lone pair into a bonding pair. Now with 1, 2, 3, 4, then the lone pair 5, 6. That formal charge has disappeared, so it's now controlling 6 electrons from the 10 which are around it. So that's our final answer. We know to stop with the hypervalent elements because we get rid of that formal charge. Because there is some formal charge still in the molecule because of the charge there. That's the single bonded oxygens with a -1 charge each time. They should control 6, but they control 2, 4, 6, and 1 in the bond, 7, giving us -1. So hypervalence just gives us an extra step. We keep going as long as we're within the limits for the element's hypervalency and get rid of that formal charge on the hypervalent atom itself. Let's take a look at some examples of molecules with multiple atoms at the center, because we see some very complex molecules in medicine, like DNA with hundreds and thousands of atoms strung together like a backbone to the molecule. And so we want to look at some modest examples like that. And so we'll do hydrazine and hydroxide on this page. And we'll just build it up in exactly the same way as we normally would. So electron count, our first step, that's 1 electron for each hydrogen, and there's 2 of them. 6 electrons for each oxygen, and there's 2 of them. So that gives us a grand total of 14. Choosing the central atom, hydrogen has got 1, it needs another to have a duet like helium. Oxygen has 6, it needs 2 more to have a octet like neon. So needing more electrons, oxygen should be the central atom. And we'll connect it to the other atoms, specifically to the other oxygen, just as we normally would. So we're down to 12 electrons. We connect the remaining atoms around the two central atoms as evenly as we can. Two atoms at the center, so we divide the two hydrogens between those two central atoms. Neither oxygen is more central than the other. So that's used another 4 electrons, takes us down to 8. We'll use the remaining electrons to complete octets, but of course hydrogen, wanting a duet like helium, already has its shell with those two bonding electrons. So the lone pairs go on the oxygens, and with 2 lone pairs each, 4 electrons, together with the bonding pairs, 2, 4, 6, 8, that each oxygen sees, 2, 4, 6, 8. Both of the oxygens now have an octet. So we have the final Lewis structure. No hypervalency for a for a period 2 element. Hypervalent elements only get to work with more electrons than 8 because they're putting electrons into the 3D subshell. An element in the second row only has 2 shells, doesn't have access therefore to any 3D third shell or subshells. Next one, hydrogen. Let's quickly do this one as well. Again, electron count, 5 for a nitrogen, based on its position in the periodic table, 5th element in the row. There's 2 of them, plus 1 for each hydrogen, and there's 2 of those. So we get 12 in total. Nitrogen needs 3 to make 8. Hydrogen only needs 1 more to make 2, like helium. So the nitrogens go to the center, and just as we did with the peroxide, we put the nitrogens at the center, connected by a bond. Everybody's got to be connected by a bond. And then we add on the hydrogens, 1 apiece, as we did before with the peroxide. That takes away another 4 electrons, so we're down to 6. Hydrogens have duets, so they're happy. And so we use the 6 remaining electrons to start creating lone pairs. But we run out of electrons to make lone pairs before we can complete the octet of the second nitrogen, only 2, 4, 6. That is not going to work for a nitrogen atom. And so we invoke our last rule and use a bonding pair and turn it into a lone pair. A lone pair and turn it into a bonding pair. I beg your pardon. Apparently I didn't have enough of a nap today. So now everybody has their octet and duets. 2, 4, 6, 8 for each nitrogen. 2, 4, 6, 8 for the nitrogen. And then 2 for each hydrogen. Everybody's happy. Everybody is stable. Now, just before we look at something else, it's worthwhile mentioning that sometimes molecules which exist do defy the octet rule with not enough electrons to complete their shell, but are still stable. And a good example of that is the element boron, which repeatedly offends this rule and doesn't have an octet. Borane with boron is a good example, BH3. So 3 electrons for the boron, 1 for each hydrogen, so a total of 6. We'll put boron at the center because it needs more electrons for its shell, certainly compared to a hydrogen. We connect the hydrogens to the boron with a chemical bond each time, using 2 electrons, which uses up our supply, but we can't complete the octet of the boron, just 2, 4, 6. And that's all we can do. There's an empty orbital on the boron. And so we can use that orbital to receive electrons from electron-enriched chemicals, which are negatively charged, to form chemical reactions. And so despite having that incomplete octet, that empty orbital on the boron does explain why borane and molecules like it with boron are so highly reactive, because they're desperately looking for electrons to complete their shell. Okay. There were some polling questions that we did with the students in class, because nobody here just now. Let's see, naming compounds. So naming of compounds is pretty similar to what we had done before with ionic compounds, but because chemists are jerks, we'd make it a little bit different. So let's take a look at that. So with a chemical like containing phosphorus and chlorine, what we quite often find is that the most metal-like substance is named first. So as we look at phosphorus and chlorine, remember a divide through the metalloids between metals and non-metals. Goes from boron, let's use some color here. Goes from boron down to the right. That hits the majority of the metalloids. And to that we just add germanium and antimony. Then excluding hydrogen, everything else to the left is a metal. Everything to the right of that divide is a non-metal. And so we can argue and say that the phosphorus, as we look at it, we can say that it's more metal-like than chlorine because it's closer to the metal side of the table. And normally it's the metal or the most metal-like substance which is listed first in the formula. There we go, couldn't find the clear button there. So the most metal-like substance is listed first normally. And the name of that element is just left as normal. So phosphorus is still phosphorus. That's kind of like what we did for the ion chemistry as well, where sodium was still sodium, calcium was still calcium, gallium was still gallium. And the only exceptions to that was when we had a transition metal with the us and ik. So the first element listed is still the full name. It's the latter element which has its name changed to IDE. So chlorine becomes chloride. The latter element changes to IDE, as we saw in ion chemistry, except for, of course, the polyatomic ions. But just a simple element changes to IDE. That's again what we had seen before in ion chemistry. But what's different now is that the number of atoms for that element are now important. And we list the number of atoms in the chemical formula. We, of course, didn't do that for ionic compounds. So if we had something like aluminium chloride, which of course is AlCl3, it's just aluminium chloride, no mention of the 3 chlorides there. But now with PCl3, that was our formula, we have to mention those 3 chlorine atoms. So we put this prefix of trichloride into the name of the molecule. So phosphorus trichloride for the full name. If there's 2 atoms of that element, we put in a di. 4 would be tetra, like a tetrahedron with 4 sides, or a pentagon with 5 sides, hexagon with 6 sides, heptagon with 7 sides, octagon with 8 sides, or octa for the prefix. Then we have nona for 9 and deca for 10. That's as far as we'll take it. I wouldn't expect you to name compounds with 12, 18, 22 or more. Just the first 10. We are doing an introductory course after all. Okay, so let's take a look at some examples based on those ideas. Remember, most metal-like element first. If it is a metal, then you're probably talking about an ionic compound. That's the easiest way to differentiate between covalent and ionic. Covalent compounds don't contain metals. So silicon and oxygen, giving us silicon dioxide. Phosphorus with sulfur in a 2:5 ratio, so diphosphorus, pentasulfide. A 2:4 ratio for nitrogen and oxygen, dinitrogen, name ending isn't changed. Tetroxide from tetra, there's a vowel clash, so we take the A out. Carbon with 4 chlorines, so carbon tetrachloride. Sulfur with 3 oxygens, so sulfur trioxide. Phosphorus and hydrogen in a 4:10 ratio, so tetraphosphorus decahydride. Sulfur with 6 fluorines, so sulfur hexafluoride. Let me get down the list a bit further. Oops. Then boron with chlorine, 2:6 ratio, diboron hexachloride. Oxygen difluoride, OF2, and carbon disulfide, CS2. So most metal-like element listed first, name goes unchanged, the latter is always changed, and then we have to list how many of that element is present in the formula. Okay, that takes us on to shapes of molecules, stepping up the trickiness a little bit. So we're looking at the electron pairs which are around the central atom, these bonding pairs, and looking at how those electron pairs which are negatively charged repel other electron pairs which are negatively charged. It's like a bunch of people at your party who all despise each other, and they're trying to keep as far away from each other as possible, keep that distance. And so if one person moves over to one side of the room, the people on that side of the room have to act and then move away somehow. I often think about it like satellites around the planet. So if we draw the planet Earth, let's see, let's make it blue. And actually, just before I do that, let me give myself some space. So badly drawn, we have planet Earth. And then of course, in the 20th century, there was a great space race and satellites started to go up around the planet. First satellite goes up from the Russians, the first satellite. Doesn't have to worry about anything. There's nobody else up there. But once the Americans get a satellite up, that second satellite goes up, and if it's a prime directive for them to avoid each other in space, they would take up an orbit that would put them on the opposite sides of the planet, going through the center of the planet to get to those two satellites as quickly as possible. That gives us a linear shape. If a third satellite went up, 3 altogether, again, if it was a prime directive, getting my Star Trek out there, to avoid each other, then the 3 satellites would take up the shape of a triangle as they maintain orbit. If there was a 4th satellite up, probably up by the British, so that was the one that was done properly and worked. Again, as they try and avoid each other as geometrically as possible, Then we've got the points of a square. Likewise, if there were 5, they'd be the points of a pentagon. Or if it was 6 satellites in space trying to avoid each other, it'd be the points of a hexagon. You get the idea. This is what we're going to start talking about on Monday with our online lecture. Remember, we're normally on campus on Monday, but it's going to be online at 11 o'clock in the morning. We're going to talk about how these electron pairs repel each other, and as the electron pairs move to positions to avoid each other, if it's a bonding pair, it's carrying the atom that it's bonded to with it. So if you're talking about my shoulder and my fist, and then in the middle here, I actually try and move my elbow. Wherever I move my elbow, because my hand is joined onto the elbow by the arm, like a chemical bond, wherever the elbow goes, the hand has to move with it. And so as bonding pairs move away from other electron pairs, it could be bonding pairs or lone pairs, as they move away, it's moving the atoms, and it's therefore creating very particular shapes. And we'll talk about those shapes on Monday and do some more Lewis structures. The only thing to keep in mind is that when we're drawing these Lewis structures with these shapes, if we've got a double bond or a triple bond, treat that double or triple bond like a single group of electrons, because they've got to be shared in that mutual space. So we treat them like one single entity. So a molecule with a central atom, which had, I'll just use a point here, we had a double bond and a single bond and another single bond, they'd have to take up positions to avoid each other, those 1, 2, 3 bonds. Or if there was a triple bond around the central point and one other bond to make the octet, if we get as far away as possible from the triple bond as it can, and that therefore creates a very particular shape as the atoms move with the bonding electrons. Anyway, more about that on Monday. That's all for today. So remember, my babysitter has gotten quarantined. So campus lecture will be Wednesday next week, and online lecture will be Monday and Friday. Okay? Right. Take care, guys. Don't be like my babysitter. Keep your guard up. Every week, we've got 1 or 2 new cases of COVID-19 in 141 and my other classes. Keep your guard up. Now is not the time to start slacking, not wearing a mask, or not socially distancing, or going to events that you don't really need to attend. Okay? Hang in there, guys. I'll talk to everybody on Monday.